Hello. Today we'll study the differentiation of exponential functions. Let's get straight to the point. The formula you are currently looking at is the differentiation formula for exponential functions. It may look slightly different from the formulas you're familiar with, right? The derivative of a to the power of box is obtained by dividing the base a raised to the power of box, multiplying it by the derivative of the box, and finally, multiplying by ln a. If the base value is e, then the multiplication by ln a becomes ln e, which is equal to 1. Therefore, it simply disappears. The reason I explain the differentiation of exponential functions in this way is simple. Many people perceive cases with a base value of e and the cases without e as separate problems and use different methods for each. However, by using this formula, you can differentiate exponential functions regardless of the base value being any constant. Today, let's solve these 5 examples together and learn the differentiation of exponential functions in various cases. Shall we get started? The first example is y equals 10 to the power of 5x squared minus 7x. To find dy over dx, let's apply the differentiation formula we learned earlier. Since the base value in the problem is 10, the value of a in this formula should also be 10. Let's substitute a with 10 in the formula. The last value will be ln 10. Now, let's compare this formula with the problem and determine what should be placed in the white box. We need to put 5x squared minus 7x in the left white box and also in the right white box. Then in the green box prime, we need to put the derivative of 5x squared minus 7x, which is 10x minus 7. Now, let's simplify and write the answer. Dy over dx equals 10 to the power of 5x squared minus 7x times 10x minus 7 times ln 10. We found the answer easily. In the next example, we'll solve the differentiation of the exponential function with the trigonometric functions involved. The next problem is y equals e to the power of sine x plus cosine x. Again, let's use the formula shown in the top right corner and substitute the base value of e into a. If we substitute a with e, the last term ln e becomes 1 and disappears. Now let's put sine x plus cosine x in the right box as the exponent of the problem, and also put sine x plus cosine x in the right box. Since box prime represents the derivative of the white box, we'll put derivative of sine x plus cosine x, which is cosine x minus sine x, in the green box prime. We have our answer. Simplifying it, we get e to the power of sine x plus cosine x times cosine x minus sine x. To summarize, we found that the derivative of e to the power of box is e to the power of box times box prime. Now, what happens if we integrate e to the power of box times box prime? Naturally, we should get e to the power of box. Let's use the derivative we just found to perform the integration. Putting sine x plus cosine x in the left box and cosine x minus sine x in the box prime, the integral simply becomes e to the power of sine x plus cosine x plus c, where c is an arbitrary constant of integration. Let's look at one more simple example. Here we have the exponential integration formula again, and this time we'll put x squared in the box and 2x, the derivative of the x squared, in the box prime. In this case, the integral of function becomes simply e to the power of x squared plus c. I've shown you a glimpse of the exponential function integration. If you understand the differentiation formula we are learning together for exponential functions, you'll be able to perform exponential integration without substitution, making it much easier and faster. If you want to learn more details, click on the link in the top right corner. Let's solve the third example, y equals 2 to the power of x plus 3 plus 3 to the power of 2x right away. The derivative of the first term, 2 to the power of x plus 3, is obtained by multiplying it with the derivative of x plus 3, which is 1, and then multiplying it by ln 2. Similarly, for the second term, we write down 3 to the power of 2x, multiplying by the derivative of 2x, which is 2, and then bring in the base value of 3 to create ln 3 and multiply it. This gives us the answer. To summarize the answer, dy over dx equals 2 to the power of x plus 3 times ln 2 plus 3 to the power of 2x times 2 ln 3. We solved it very simply, didn't we? In the next example, let's tackle a more complex problem using the quotient rule. The problem at hand is y equals x over 3 to the power of x squared. To find dy over dx, we need to apply the quotient rule. Using the quotient rule formula, dy over dx can be written as x prime times 3 to the power of x squared minus x times 3 to the power of x squared prime all over 3 to the power of x squared and complete squared. The part we need to focus on is the derivative of 3 to the power of x squared. Let's first bring the derivative of formula and substitute 3 for all the instances of a in the formula. Then we'll put x squared in the left box and also in the right box. Now let's put the derivative of x squared, which is 2x in the green box prime. With this, our calculation is complete. Now we substitute the derivative we found using the quotient rule into the result. We get dy over dx equals 1 times 3 to the power of x squared minus x times 2x ln 3 times 3 to the power of x squared all over 3 to the power of 2x squared. Simplifying the numerator a bit, it becomes 3 to the power of x squared minus 2x squared times ln 3 times 3 to the power of x squared all over 3 to the power of 2x squared. Now let's solve the last example. This example not only involves the box rule for derivatives, but also allows us to utilize the modified power rule that I explained in another video, making it very easy to find the solution. Alright, let's proceed with the problem. We have y equals 4 to the power of tangent x minus 1 to the power of 3. Before considering the exponential function, we notice that there is an exponent of 3 applied to the entire expression. It seems reasonable to start by differentiating the outermost exponent. So let's first recall the modified power rule that I introduced in another video. If you want to learn more about this formula, you can click on the link in the top right corner for detailed explanations and examples. Now, comparing this formula with our problem, we can see that the term 4 to the power of tangent x minus 1 goes inside the box, and the exponent value n is 3. We'll put 3 in the right hand end position, and then we'll put 4 to the power of tangent x minus 1 inside the box. The exponent of the box will be written as 3 minus 1. Next, we need to determine the derivative of the box and put it in the box prime. To differentiate 4 to the power of tangent x minus 1, we only need to focus on differentiating 4 to the power of tangent x. The formula for differentiating exponential functions, as shown in the upper right corner, indicates that we should replace all the instances of a with 4. So the left a becomes 4, and the right a and the natural logarithm both becomes 4 as well. Now let's fill in the values for the box and the box prime. We'll write tangent x in the left box, which is the same as the term in the problem, and we'll do the same for the right box. As for the green box prime, we can simply input the derivative of tangent x, which is secant square x. By substituting the differentiated values into the respective box and the box prime, we obtain 4 to the power of tangent x times secant square x times ln 4 for the green box prime. Let's summarize the answer. dy over dx equals 3 times 4 to the power of tangent x negative 1 to the power of 2 times 4 to the power of tangent x times secant square x times ln 4. How was today's lesson? It is not just about teaching these methods for the sake of differentiation. Understanding how the differentiation of exponential functions works can also make it much easier to comprehend and solve the integration of the exponential functions. I strive to create videos that help with your mathematics learning. If today's video has been helpful to you, please consider subscribing and liking. Thanks for watching, and this has been your Math Guardian, Alex.